Hey, welcome back to Chemistry with Mrs. Mays. Today we're going to look at solution stoichiometry. So we'll be calculating amounts of moles in balanced equations and applying them to solutions. So first it's important to understand that molarity can be used as a conversion factor in dimensional analysis, like in your T-table. In this first example, example 1, the question asks how many moles of nitric acid are in a 2-liter solution of 0.2 molar nitric acid. So the way we change moles to liters is, first of all, when we see this big M, I'm going to cross it out, because what it means is how many moles are there in 1 liter. So I'm just going to change the big M to moles over liters. Now let's solve the problem. I have 2 liters of solution, and I know that for every 1 liter of my solution, there's 0.200 moles. See, what I've done is to change the big M for molarity into moles over liters. So now we just do the math with our calculator. 2 liters times 0.2 molar, and I get 0.4. I did not need a calculator for that. So I get 0.40, looks like I only get to keep 2 sig figs. 0.40 moles of nitric acid are in that solution. Put a box around your answer so your teacher can find it, and we're good to go. This is one of the important steps that we'll use when we deal with solution preparation. One of the things that we'll need to be able to do is to create a solution to the specified molarity. So the first thing you have to do is weigh out the grams of your substance. How many grams? Well, that depends on how many moles. So the weight depends on how many moles you want. Use your molar mass for that. Then the next thing we'll do is dissolve that powdered solute in some of the water. I like to add the water, a little bit of water to the flask before I put this stuff in, because sometimes it generates heat to dissolve, and I want the water there to absorb that heat. Then we get it all to dissolve completely, and then you'll be filling up to a mark in your volumetric flask, and make sure that you read from the bottom of the meniscus, because if you overfill it past the mark, you have to start all over again and throw out some perfectly good chemicals. So be very careful when you're filling it up to that mark. Don't go past. And that's how we would prepare a solution. Here's one example. How many grams of hydrochloric acid would be required to make a 50 milliliters of a 2.7 molar solution? And remember, this is HCl, so really what I need to know first is moles. When in doubt, go to moles. I can find the number of moles if I change the capital M for molarity into moles over liters. Now I know liters is on the bottom. If I multiply by liters, I can get my moles, right? And I have 50 milliliters. So let's see, if I have 50 milliliters and I move my decimal 3 times over, then I can convert it from milliliters to liters, right? And I want my solution to consist of 2.7 moles of HCl for every liter of my solution. And then my final step is to get to grams. Notice how liters cancels away, so I'm at moles now. Remember how to change moles to grams? Right, we're going to use the molar mass. Hydrogen is 1 and chlorine is 35.5. So let's add those two together. So that's 36.5 grams per mole. Then we work out the math. Time for a calculator. So I had 0.050 times 2.7 times 36.5 grams per mole. And we divide by the bottom, which is just 1. So I need 4.93. How many sig figs do we get to keep? Looks like just 2. So we'll call that 4.9 grams of HCl. And make sure you put a box around it. And you got the number of grams to weigh out in that very first step so that you can make your solution. So with solution stoichiometry, you may have noticed already, if we take the volume times the molarity you're going to get moles. This is super important because getting to moles is one of our first goals in solving a stoichiometry problem. Then we'll use the mole ratio in our balanced equations to calculate the amounts of substances that are in the aqueous reactions. So let's look at another example. In example 3, it asks us to calculate the mass of barium sulfate that's formed when excess 0.2 molar sodium sulfate solution is added to 0.5 liters of 0.5 molar barium chloride solution. Well, the first thing I need is a balanced equation, so let's write that up here. I have sodium sulfate solution. And notice that they tell us which thing is in excess, so we don't have to do a limiting reagent problem. And that's being added to barium chloride. And that will form, in a double replacement reaction, sodium chloride and barium sulfate. Now let's balance this equation. So let's see, I need 2 sodiums and 2 chlorines. There we go, balanced equation. And now I can work the stoichiometry problem that's given. My easiest way to get to moles is to take volume times molarity. Here we go, right here. So I take 0.50 liters of barium chloride, and I'm going to multiply that by molarity in my T table, because remember, a big M means how many moles are there in a liter. So that will put my 1 liter crisscross from the liters I had before. That's 0.500 moles of barium chloride. Now I have to use my mole ratio. I got to moles of barium chloride, but what I want is barium sulfate. So let's use our balanced equation. For every 1 mole of barium chloride, I need 1 mole of barium sulfate. Now I need the molar mass of barium sulfate, so I need my periodic table. So barium weighs 137.3 grams per mole, and sulfur is 32.1-ish. And then oxygen, of course, is 16. You guys probably have that one memorized. Okay, check my math, as always, because I can make mistakes. I got 233.39 grams for every mole of barium sulfate. So it's calculator time. So we had 0.5 liters times 0.5 molar times the molar mass of 233.39 grams per mole, and then divide by the bottom, which is all just 1, and we got 58.35. How many sig figs? Let's see, 3 sig figs. So we'll call that 58.4 grams of barium sulfate will be formed in this reaction. And the sodium sulfate didn't even get entered into the equation because it was in excess. That's not the thing that's going to determine how much barium sulfate is formed. It's the limiting reagent, the barium chloride, that determined how much product we can create. All right, so that's how we work with stoichiometry, and that's how we use stoichiometry to solve solution problems. That's it for now, and that's the most math we're going to do in this unit. So I'll see you guys very soon.